Okay. Good afternoon. My name is Jose Luis. I'm going to present part of my work uh, that we have been developing with Dr. Minerva. The presentation is entitled Molecular Dynamics about nuclear nanotubes in explicit water. So first, we know that the nanometric structure is on the order of the 10 to minus 9 meters, and these nanostructures can be classified depending on their morphology like nanoparticles whose dimension is zero, nanotubes with dimension is one, and nanosheets with dimension is two. In this work, we focus on nanotubes. Nanotubes are characterized by Hamada index. This can be zigzag, unchaired, or hidden. We carry on our study using boron nanotubes, which were predicted by Robio, Corke, Cohen in 1994, since they have a very similar structure to carbon nanotubes. They have been proposed for different applications due to the properties of this type of nanotubes. They have been proposed for medical, mechanical, electronic, but also biomedical applications. And they have been proposed for the encapsulation and delivery of drugs, for the transport of water through these nanotubes, and recently for the purification or treatment of wastewater, among others. Several of these applications are developed in aqueous media, which is why our study by uh, boron-induced nanotubes in water becomes important. So we perform this study numerically using molecular dynamics, whose, whose goal is to solve the equation of motion of any interacting particles in a system at successive instant of time. That is, we chose an ensemble, the interaction potential, the initial condition, initial position and velocities, number of particles, volume, temperature, pressure. Subsequently, the calculation of the force is made for this integration algorithm are used. The time evolution is performed to obtain the new positions and new velocities. At the end of the cycle, we perform an analysis of the results. That is, we calculate the physical properties of the system. And molecular dynamics present its solution naturally in macroeconomical ensemble. However, this is difficult to do experimentally. Therefore, a chain of ensemble is made, choosing, for example, the canonical or isothermal isobaric ensemble, in which it requires to maintain constant temperature and or pressure. Uh, for this, molecular dynamics makes use of thermostats and barostats that help use keep these properties fixed in systems. To develop these studies, there are several simulation pages. We use special Groma space. For this, it's necessary to have the necessary parameters to model water molecules and nanotubes. These parameters are somatic heat. For the water, they are used from the SPC epsilon model, while the nanotubes we take them from the literature. And in this work, we use a zigzag type nanotube whose index are 60, and the length of the nanotube is 1591 Angstrom. So we now present our first result of nanotubes in explicit water. For this part, we perform simulation on the NPT ensemble, where we have used the Benson thermostat and barostat. In addition, we vary the concentration of nanotubes in water, so our results are for the three different concentrations. In the figures, we show a snapshot of the system for the concentration of the 0.11 mol per kilogram. The figure on the left is the system in its initial state, while the figure on the right is the final state. After running the simulation, we calculate some properties of interest In our case, we calculate the radial distribution function. So where it provides information about the structures and average distribution of the molecules in the system. Since the radial distribution function is related to the probability and finding a second particle at a distance r measured from a reference particle. In this case, we show the effects of the concentration of nanotubes in the system. In the case of boron atoms, the peaks of the function are mainly generated by the atoms of the same nanotube. We notice that as the concentration increases, the values of these peaks decrease. This is because there are increase in the number of atoms, and this increased case causes the boron atoms to be further away from each other. Furthermore, as we have set the pressure at 1 bar, and for this to be maintained, the volume has to increase as the concentration of nanotubes increase, and this is what is observed in this graph. Otherwise, with water molecules, as we observe for oxygen atoms, there is a slight increase in the radial distribution function. That is, the water molecules are closer to each other when we increase the concentration of nanotubes. And now we calculate the correlation between atoms of nanotubes and water. Uh, as can be seen in the figure, this correlation is very low, and as the concentration increases, this correlation decreases even more since the volume increases in the order to maintain the constant pressure, thus generating an even greater space between the water molecules and the nanotubes. Another property that we calculate is the static dielectric constant. This is calculated by the fluctuation of the dipole moment of the system. As water is a polar molecule, and has a high value of the dielectric constant, the experimental value is um, 78.5, and the one obtained by the numerical simulation is 79.32. This value is obtained in this work, and this is 1% larger than the experimental value. So now we calculate the value of the electrical constant for the mixture, and we compare how much is the change with respect to the pure water. In general, we observe the increase in the value of the electric constant since the charge distribution in zigzag type nanotubes is like the of the dipole, and also the average dipole moment possessed by the nanotubes is relatively high. So this contributes to the increase in the value of the electric constant. This physical quantity determines the ability of the material to become polarized in the presence of an electrical field. So this mixture favors this polarization. Um, so another part of results in is the liquid vapor coexistence. We this we do this in MBT ensemble uh, to keep the temperature fixed. We use the Master-Huber thermostat. We also consider three different concentrations. Each concentration we perform in several simulations at different specific temperatures. As we show in the figures, the fields located in the upper right part of the capture of the initial configuration for the concentration of 0.22 mole per kilogram. The following image is when the simulation is performed at 300 Kelvin, thus having a denser region, which is the liquid phase, while the less dense one is the vapor phase. The last figure is for a temperature of 500 Kelvin, at which we can observe more molecules in the vapor region. To obtain the coexistence curve, we first compute the density profiles of the different simulation and specific temperature. This is done using the slab method, and we consider slicing the cell into different slabs and calculate the density. As we see in the upper left figure, it is the final configuration of system. In particular, 400 Kelvin at the calculated density for this system is shown in the lower graph, which contains the contribution of the nanotubes that are the green line. The red one is from the water molecules, and by adding the two contributions, we get the black cube, which is the density profile of the entire system. This is done for the different configuration to build the coexistent cube, as I show in the right figure. The black cube is the experimental obtained coexistent cube for the pure water. The blue cube is for the concentration of 0.028 mole per kilogram, which at temperature less than or equal to 550 Kelvin is very similar to that of pure water. Only at high temperatures there is a small increase in the density. This is due to the nanotubes that increase the density. In the red cube, it is for the next concentration in the liquid branch that it is displaced since as the concentration of nanotubes increase, the density in the liquid region increase, increases. But at temperature of 550 Kelvin, the values are very similar to that pure water, since the nanotubes favor this displacement of water molecules to the vapor region. A similar behavior is observed at the highest concentration, only that at temperatures above 500 Kelvin, the phase distinction is not very clear. Meanwhile, we can also observe this calculating the surface tension, as we see in the figure of the left. We have the less dense region that are the part of the vapor phase and the one that is denser in the liquid phase. And the little region where we go from the one phase to another is the interface. So we calculate the surface tension for the three concentration and compare them with the surface tension of pure water obtained in this simulation work. We observe that as has the concentration increased, the surface tension decreased. That is to say that the nanotubes favor the movement of the water molecules from the liquid phase to the vapor phase. As the temperature increases, it becomes a tensive mixture. However, we notice that the red cube for the temperature of 60, 615 Kelvin increase, but they still cannot ensure that it is correct because we couldn't correctly determine the values of the liquid and vapor phase. Similarly, for the highest concentration at temperatures above 550 Kelvin, they give a negative values, but they are not correct because the interface can be distinguished at these temperatures. So, uh, conclusion of these results, we have the SPC Epsilon water model was correctly implemented in the numerical simulation, since the electrical constant and surface tension are in good agreement with the literature. For the radial distribution function, we observe the effect on the concentration of nanotubes in water, how the volume increase to maintain the fixed pressure, and this generates a lower interaction of atoms of one nanotube with that other. So the water got closer to each other, and the water nanotubes, the water um, molecules and nanotubes correlation is very low because boron in two nanotubes are no water soluble. Uh, in the electrical constant, we extend the simulation time to see the green curve converge to a value. And for the coexistence, we have to develop a formal simulation to determine if the concentration we have considered are adequate for the description or if the system is saturated with nanotubes. Yes, in the surface tension for the lowest concentration, the behavior is similar to the pure water, although slightly lower. So, I acknowledge al Laboratorio Nacional of Supercómputo, CONOCID, and the VIEF. And thank you.